Wetting. Wetting is the ability of a liquid to maintain contact with a solid surface resulting from intermolecular interactions when the two are brought together. This happens in presence of a gaseous phase or another liquid phase not miscible with the first one. The degree of wetting wettability is determined by a force balance between adhesive and cohesive forces. Wetting is important in the bonding or adherence of two materials. Wetting and the surface forces that control wetting are also responsible for other related effects, including capillary effects. There are two types of wetting: non-reactive wetting and reactive wetting. Wetting deals with three phases of matter: gas, liquid, and solid. It is now a centre of attention in nanotechnology and nanoscience studies due to the advent of many nanomaterials in the past 2 decades, e.g. graphene, carbon nanotube, boron nitride nanomesh. Explanation. Adhesive forces between a liquid and solid cause a liquid drop to spread across the surface. Cohesive forces within the liquid cause the drop to ball up and avoid contact with the surface. Thumb upright equals 1.25 Figure 2. Wetting of different fluids. A shows a fluid with very little wetting, while Celsius shows a fluid with more wetting. A has a large contact angle, and Celsius has a small contact angle. The contact angle theta, as seen in Figure 1, is the angle at which the liquid-vapor interface meets the solid-liquid interface. The contact angle is determined by the balance between adhesive and cohesive forces. As the tendency of a drop to spread out over a flat, solid surface increases, the contact angle decreases. Thus, the contact angle provides an inverse measure of wettability. A contact angle less than 90 degrees, low contact angle usually indicates that wetting of the surface is very favourable and the fluid will spread over a large area of the surface. Contact angles greater than 90 degrees high contact angle generally mean that wetting of the surface is unfavourable, so the fluid will minimise contact with the surface and form a compact liquid droplet. For water, a wettable surface may also be termed hydrophilic and a non-wettable surface hydrophobic. Superhydrophobic surfaces have contact angles greater than 150 degrees, showing almost no contact between the liquid drop and the surface. This is sometimes referred to as the lotus effect. The table describes varying contact angles and their corresponding solid/liquid and liquid/liquid interactions. For non-water liquids, the term lyophilic is used for low contact angle conditions and lyophobic is used when higher contact angles result. Similarly, the terms omniphobic and non-aphilic apply to both polar and apolar liquids. High energy vs. low energy surfaces. Liquids can interact with two main types of solid surfaces. Traditionally, solid surfaces have been divided into high energy and low energy solids. The relative energy of a solid has to do with the bulk nature of the solid itself. Solids such as metals, glasses, and ceramics are known as hard solids because the chemical bonds that hold them together, e.g., covalent, ionic, or metallic, are very strong. Thus, it takes a large amount of energy to break these solids. Alternatively, a large amount of energy is required to cut the bulk and make two separate surfaces, so they are termed high energy. Most molecular liquids achieve complete wetting with high energy surfaces. The other type of solid is weak molecular crystals, e.g., fluorocarbons, hydrocarbons, etc., where the molecules are held together essentially by physical forces, e.g., van der Waals forces and hydrogen bonds. Since these solids are held together by weak forces, a very low amount of energy is required to break them, thus they are termed low energy. Depending on the type of liquid chosen, low energy surfaces can permit either complete or partial wetting. Dynamic surfaces have been reported that undergo changes in surface energy upon the application of an appropriate stimuli. For example, a surface presenting photon-driven molecular motors was shown to undergo changes in water contact angle when switched between bistable conformations of differing surface energies. Wetting of low-energy surfaces. Low-energy surfaces primarily interact with liquids through dispersive van der Waals forces. William Zisman produced several key findings. Zisman observed that cos theta increases linearly as the surface tension gamma LV of the liquid decreased. Thus, he was able to establish a linear function between cos theta and the surface tension gamma LV for various organic liquids. A surface is more wettable when gamma LV and theta is lower. Sussman termed the intercept of these lines when cos theta equal 1 as the critical surface tension gamma c of that surface. This critical surface tension is an important parameter because it is a characteristic of only the solid. Knowing the critical surface tension of a solid, it is possible to predict the wettability of the surface. The wettability of a surface is determined by the outermost chemical groups of the solid. Differences in wettability between surfaces that are similar in structure are due to differences in the packing of the atoms. For instance, if a surface has branched chains, it will have poorer packing than a surface with straight chains. Lower critical surface tension means a less wettable material surface. Ideal solid surfaces. An ideal surface is flat, rigid, perfectly smooth, chemically homogeneous, and has zero contact angle hysteresis. Zero hysteresis implies the advancing and receding contact angles are equal. In other words, only one thermodynamically stable contact angle exists. When a drop of liquid is placed on such a surface, the characteristic contact angle is formed as depicted in Figure 1. Furthermore, on an ideal surface, the drop will return to its original shape if it is disturbed. The following derivations apply only to ideal solid surfaces. They are only valid for the state in which the interfaces are not moving and the phase boundary line exists in equilibrium. Minimization of energy. 3 phases. Figure 3 shows the line of contact where 3 phases meet. In equilibrium, the net force per unit length acting along the boundary line between the 3 phases must be 0. The components of net force in the direction along each of the interfaces are given by $begin align \gamma alpha theta plus gamma theta beta cos left theta out plus gamma alpha beta cos left alpha out and equals 0 gamma alpha theta cos left theta out plus gamma theta beta plus gamma alpha beta cos left beta out and equals 0 gamma alpha theta cos left alpha out plus gamma theta beta cos left beta out plus gamma alpha beta and equals 0 end align $, where alpha, beta, and theta are the angles shown and gamma is the surface energy between the 2 indicated phases. These relations can also be expressed by an analog to triangle known as Newman's triangle, shown in Figure 4. Newman's triangle is consistent with the geometrical restriction that alpha plus beta plus theta equals to pi, and applying the law of sines and law of cosines to it produce relations that describe how the interfacial angles depend on the ratios of surface energies. Because these 3 surface energies form the sides of a triangle, they are constrained by the triangle inequalities gamma h, gamma jk plus gamma h, meaning that not one of the surface tensions can exceed the sum of the other 2. If 3 fluids with surface energies that do not follow these inequalities are brought into contact, no equilibrium configuration consistent with Figure 3 will exist. Simplification to planar geometry. Young's relation. Thumb upright equals 1.25 Figure 5. Contact angle of a liquid droplet wetted to a rigid solid surface if the beta phase is replaced by a flat rigid surface, as shown in Figure 5, then beta equal pi, and the second net force equation simplifies to the Young equation. Gamma Sg equals gamma Sl plus gamma Lg cos theta, which relates the surface tensions between the 3 phases, solid, liquid, and gas. Subsequently, this predicts the contact angle of a liquid droplet on a solid surface from knowledge of the 3 surface energies involved. This equation also applies if the gas phase is another liquid, immiscible with the droplet of the first liquid phase. Simplification to planar geometry. Young's relation derived from variational computation. Consider the interface as a curve x for xi equals where L is a free parameter. The free energy to be minimized is $cal f equals int 0 L left gamma Lg sqrt 1 plus y 2 plus gamma sl gamma sg out dx with the constraints as 0 equals y L equals 0, which we can write as integral x equals 0 and fixed volume integral x equals The modified Lagrangian, taking into account the constraints, is therefore $\cal L equal \gamma LG \sqrt1 plus y2 plus \gamma SL \gamma SG lambda 1 y lambda 2 y $, where lambda I are Lagrange multipliers. By definition, the momentum $p equals partial y cal L and the Hamiltonian $cal h equal py cal L, which is computed to be $cal h equal gamma LG frac 1 sqrt1 plus y2 gamma SL gamma SG plus lambda 2 y $. Now, we recall that the boundary is free in the x direction and L is a free parameter. Therefore, we must have $frac partial cal f partial L equal cal h equals 0 $, at the boundary y L equals 0 and 1 plus y2 minus 1 / 2 equals cos theta. Therefore, we recover the Young equation, non-ideal smooth surfaces, and the Young contact angle. The Young equation assumes a perfectly flat and rigid surface, often referred to as an ideal surface. In many cases, surfaces are far from this ideal situation, and two are considered here: the case of rough surfaces and the case of smooth surfaces that are still real finitely rigid. Even in a perfectly smooth surface, a drop will assume a wide spectrum of contact angles ranging from the so-called advancing contact angle, theta, to the so-called receding contact angle, theta r. The equilibrium contact angle theta c can be calculated from theta and theta r, as was shown by Tatmer as $theta mathem c equals /awkward left frac or mathema cos left theta mathema 8 plus or mathem or cos left theta mathem or 8 or mathema plus or mathem or $8 where $, or mathema equals left frac sin 3 left theta mathema 8 2 3 cos left theta mathema 8 plus cos 3 left theta mathema 8 frac 1 3 tilde or mathem or equals left frac sin 3 left theta mathem or 8 2 3 cos left theta mathem or 8 plus cos 3 left theta mathem or 8 frac 1 3 $. The Young-Dupre equation and spreading coefficient. The Young-Dupre equation, Thomas Young 1805, Anthonés Dupre and Paul Dupre 1869, dictates that neither gamma Sg nor gamma Sl can be larger than the sum of the other two surface energies. The consequence of this restriction is the prediction of complete wetting when gamma Sg gamma Sl plus gamma Lg and zero wetting when gamma Sl gamma Sg plus gamma Lg. The lack of a solution to the Young-Dupre equation is an indicator that there is no equilibrium configuration with a contact angle between 0 and 180 degrees for those situations. A useful parameter for gauging wetting is the spreading parameter S. S equals gamma Sg minus gamma Sl plus gamma Lg. When south 0, a liquid wets the surface completely, complete wetting. When south 0, partial wetting occurs. Combining the spreading parameter definition with the Young relation yields the Young-Dupre equation. S equals gamma Lg cos theta minus 1, which only has physical solutions for theta when south 0. A generalized model for the contact angle of droplets on flat and curved surfaces. With improvements in measuring techniques such as AFM confocal microscopy and SEM, researchers were able to produce and image droplets at ever smaller scales. With a reduction in droplet size came new experimental observations of wetting. These observations confirm that the modified Young's equation does not hold at the micro-nanoscales. In addition, the sign of the line tension is not maintained through the modified Young's equation. For a sessile droplet, the free energy of the three-phase system can be expressed as delta equals gamma LV dA LV plus gamma S L dA SL plus gamma SV dA SV minus capid L minus B dV minus V dP. At constant volume in thermodynamic equilibrium, this reduces to $0 equals frac d lg d sl plus frac gamma sl gamma sg gamma lg frac kappa gamma lg frac d l d sl frac v gamma lg frac dp d sl dollar. Usually, the VDP term has been neglected for large droplets, however, VDP work becomes significant at small scales. The variation in pressure at constant volume at the free liquid-vapor boundary is due to the Laplace pressure, which is proportional to the mean curvature of the droplet and is non-zero. Solving the above equation for both convex and concave surfaces yields $cos theta mp alpha equals a plus b frac cos alpha pnc sin theta mp alpha cos theta plus 1 2 biggle frac sin alpha cos alpha plus 2 cos alpha plus 1 2 mp frac sin theta cos theta plus 2 cos theta plus 1 2 bigger dollar, where the constant parameters a, b, and Celsius are defined as $I equals frac gamma sg gamma sl gamma lg $b equals frac kappa gamma lg and $c equals frac gamma 3 gamma lg. This equation relates the contact angle theta, a geometric property of a sessile droplet, to the bulk thermodynamics, the energy of the three-phase contact boundary, and the curvature of the surface alpha. For the special case of a sessile droplet on a flat surface, alpha equals 0. $cos theta equals frac gamma sg gamma sl gamma lg plus frac kappa gamma lg frac 1 frac gamma 3 gamma lg 2 plus cos the terminus 2 cos 2 theta cos 3 theta dollar. The first two terms are the modified Young's equation, while the third term is due to the Laplace pressure. This nonlinear equation correctly predicts the sign and magnitude of kappa, the flattening of the contact angle at very small scales, and contact angle hysteresis. Computational prediction of wetting. For many surface/adsorbate configurations, surface energy data and experimental observations are unavailable. As wetting interactions are of great importance in various applications, it is often desired to predict and compare the wetting behavior of various material surfaces with particular crystallographic orientations with relation to water or other adsorbates. This can be done from an atomistic perspective with tools including molecular dynamics and density functional theory. In the theoretical prediction of wetting by ab initio approaches such as DFT, ice is commonly substituted for water. This is because DFT calculations are generally conducted assuming conditions of zero thermal movement of atoms, essentially meaning the simulation is conducted at absolute zero. The simplification nevertheless yields results that are relevant for the adsorption of water under realistic conditions, and the use of ice for the theoretical simulation of wetting is commonplace. Non-ideal rough solid surfaces. Thumb upright equals 1.2 left figure 6 schematic of advancing and receding contact angles. Unlike ideal surfaces, real surfaces do not have perfect smoothness, rigidity, or chemical homogeneity. Such deviations from ideality result in a phenomenon called contact angle hysteresis, which is defined as the difference between the advancing theta and receding theta or contact angles. H equals theta minus theta r. When the contact angle is between the advancing and receding cases, the contact line is considered to be pinned and hysteretic behavior can be observed, namely contact angle hysteresis. When these values are exceeded, the displacement of the contact line, such as the one in Figure 3, will take place by either expansion or retraction of the droplet. Figure 6 depicts the advancing and receding contact angles. The advancing contact angle is the maximum stable angle, whereas the receding contact angle is the minimum stable angle. Contact angle hysteresis occurs because many different thermodynamically stable contact angles are found on a non-ideal solid. These varying thermodynamically stable contact angles are known as metastable states. Such motion of a phase boundary involving advancing and receding contact angles is known as dynamic wetting. The difference between dynamic and static wetting angles is proportional to the capillary number, Ca. When a contact line advances, covering more of the surface of liquid, the contact angle is increased and is generally related to the velocity of the contact line. If the velocity of a contact line is increased with upbound, the contact angle increases, and as it approaches 180 degrees, the gas phase will become entrained in a thin layer between the liquid and solid. This is a kinetic non-equilibrium effect which results from the contact line moving at such a high speed that complete wetting cannot occur. A well-known departure from ideal conditions is when the surface of interest has a rough texture. The rough texture of a surface can fall into one of two categories, homogeneous or heterogeneous. A homogeneous wetting regime is where the liquid fills in the grooves of a rough surface. A heterogeneous wetting regime, is where the surface is a composite of two types of patches. An important example of such a composite surface is one composed of patches of both air and solid. Such surfaces have varied effects on the contact angles of wetting liquids. Cassie Baxter and Wenzels are the two main models that attempt to describe the wetting of textured surfaces. However, these equations only apply when the drop size is sufficiently large compared with the surface roughness scale. When the droplet size is comparable to that of the underlying pillows, the effect of line tension should be considered. Wenzels model. The Wenzels model, Robert Nor, Wenzels, 1936, describes the homogeneous wetting regime as seen in Figure 7 and is defined by the following equation for the contact angle on a rough surface. Cos theta asterisk equals r cos theta, where theta asterisk is the apparent contact angle which corresponds to the stable equilibrium state, i.e. minimum free energy state for the system. The roughness ratio, R, is a measure of how surface roughness affects a homogeneous surface. The roughness ratio is defined as the ratio of true area of the solid surface to the apparent area. Theta is the young contact angle as defined for an ideal surface. Although Wenzels' equation demonstrates the contact angle of a rough surface is different from the intrinsic contact angle, it does not describe contact angle hysteresis. Cassie Baxter model. When dealing with a heterogeneous surface, the Wenzels model is not sufficient. A more complex model is needed to measure how the apparent contact angle changes when various materials are involved. This heterogeneous surface, like that seen in Figure 8, is explained using the Cassie-Baxter equation, Cassie's law. Cos theta asterisk equals RFF cos theta y plus F minus 1. Here the RF is the roughness ratio of the wet surface area and F is the fraction of solid surface area wet by the liquid. It is important to realize that when F equal 1 and RF equal R, the Cassie-Baxter equations becomes the Wenzels equation. On the other hand, when there are many different fractions of surface roughness, each fraction of the total surface area is denoted by Fi. A summation of all Fa equals 1 or the total surface. Cassie-Baxter can also be recast in the following equation. $$ gamma cos left theta asterisk. 8 equals sum n equals 1 n fa left gamma text isc gamma text isl. $8. Here gamma is the Cassie-Baxter surface tension between liquid and vapor, gamma I SV is the solid vapor surface tension of every component, and gamma I SL is the solid liquid surface tension of every component. A case that is worth mentioning is when the liquid drop is placed on the substrate and creates small air pockets underneath it. This case for a two-component system is denoted by gamma cos theta asterisk equals F1 gamma 1 SV minus gamma 1 SL minus 1 minus F1 gamma. Here the key difference to notice is that there is no surface tension between the solid and the vapor for the second surface tension component. This is because of the assumption that the surface of air that is exposed is under the droplet and is the only other substrate in the system. Subsequently, the equation is then expressed as 1F. Therefore, the Cassie equation can be easily derived from the Cassie-Baxter equation. Experimental results regarding the surface properties of Wenzels versus Cassie-Baxter systems showed the effect of pinning for a young angle of 180 to 90 degrees, a region classified under the Cassie-Baxter model. This liquid/air composite system is largely hydrophobic. After that point, a sharp transition to the Wenzels regime was found where the drop wets the surface, but no further than the edges of the drop. Actually, the Young, Wenzels and Cassie Baxter equations represent the transversality conditions of the variational problem of wetting. Precursor film. With the advent of high-resolution imaging, researchers have started to obtain experimental data which have led them to question the assumptions of the Cassie Baxter equation in calculating the apparent contact angle. These groups believe the apparent contact angle is largely dependent on the triple line. The triple line, which is in contact with the heterogeneous surface, cannot rest on the heterogeneous surface like the rest of the drop. In theory, it should follow the surface imperfection. This bending in the triple line is unfavorable and is not seen in real-world situations. A theory that preserves the Cassie Baxter equation while at the same time explaining the presence of the minimized energy state of the triple line hinges on the idea of a precursor film. This film of submicrometer thickness advances ahead of the motion of the droplet and is found around the triple line. Furthermore, this precursor film allows the triple line to bend and take different conformations that were originally considered unfavorable. This precursor fluid has been observed using environmental scanning electron microscopy (ESM) in surfaces with pores formed in the bulk. With the introduction of the precursor film concept, the triple line can follow energetically feasible conformations, thereby correctly explaining the Cassie Baxter model. Petal effect vs. Lotus effect. Thumb upright equals 1.35 Figure 9. Petal effect vs. Lotus effect. The intrinsic hydrophobicity of a surface can be enhanced by being textured with different length scales of roughness. The red rose takes advantage of this by using a hierarchy of micro and nanostructures on each petal to provide sufficient roughness for superhydrophobicity. More specifically, each rose petal has a collection of micropapillae on the surface, and each papilla, in turn, has many nanofolds. The term petal effect describes the fact that a water droplet on the surface of a rose petal is spherical in shape, but cannot roll off even if the petal is turned upside down. The water drops maintain the spherical shape due to the superhydrophobicity of the petal contact angle of about 152.4 degrees, but do not roll off because the petal surface has a high adhesive force with water. When comparing the petal effect to the lotus effect, it is important to note some striking differences. The surface structure of the lotus leaf and the rose petal, as seen in Figure 9, can be used to explain the two different effects. The lotus leaf has a randomly rough surface and low contact angle hysteresis, which means the water droplet is not able to wet the microstructure spaces between the spikes. This allows air to remain inside the texture, causing a heterogeneous surface composed of both air and solid. As a result, the adhesive force between the water and the solid surface is extremely low, allowing the water to roll off easily, i.e., self-cleaning phenomenon. The rose petal's micro and nanostructures are larger in scale than those of the lotus leaf, which allows the liquid film to impregnate the texture. However, as seen in Figure 9, a liquid can enter the larger scale grooves, but it cannot enter into the smaller grooves. This is known as the Cassie impregnating wetting regime. Since the liquid can wet the larger scale grooves, the adhesive force between the water and solid is very high. This explains why the water droplet will not fall off even if the petal is tilted at an angle or turned upside down. This effect will fail if the droplet has a volume larger than 10 microL because the balance between weight and surface tension is surpassed. Cassie Baxter to Wenzels transition. In the Cassie Baxter model, the drop sits on top of the textured surface with trapped air underneath. During the wetting transition from the Cassie state to the Wenzels state, the air pockets are no longer thermodynamically stable and liquid begins to nucleate from the middle of the drop, creating a mushroom state as seen in Figure 10. The penetration condition is given by $/cos/\left\theta\phi 8 equals \frac\phi1r\phi$, where asterisk r is solid roughness for flat surface. The penetration front propagates to minimize the surface energy until it reaches the edges of the drop, thus arriving at the Wenzels state. Since the solid can be considered an absorptive material due to its surface roughness, this phenomenon of spreading and imbibition is called hemiwicking. The contact angles at which spreading/imbibition occurs are between 0 and pi/2. The Wenzels model is valid between θc and π/2. If the contact angle is less than θc, the penetration front spreads beyond the drop and a liquid film forms over the surface. Figure 11 depicts the transition from the Wenzels state to the surface film state. The film smooths the surface roughness and the Wenzels model no longer applies. In this state, the equilibrium condition and Young's relation yields cos theta asterisk equals leta 3d phi c s theta c plus 1 minus leta v d phi. By fine-tuning the surface roughness, it is possible to achieve a transition between both superhydrophobic and superhydrophilic regions. Generally, the rougher the surface, the more hydrophobic it is. Spreading dynamics. If a drop is placed on a smooth horizontal surface, it is generally not in the equilibrium state. Hence, it spreads until an equilibrium contact radius is reached, partial wetting. While taking into account capillary, gravitational, and viscous contributions, the drop radius as a function of time can be expressed as RT equal RE backslash left 1 backslash X backslash left backslash frac 2 backslash gamma LG all 12E plus backslash frac HG 9 or 10E 8 backslash frac 24 backslash lambda V4 backslash left plus T0 8 backslash pi 2 backslash eta 8 backslash frac 16. For the complete wetting situation, the drop radius at any time during the spreading process is given by RT equals backslash left backslash gamma LG backslash frac 96 backslash lambda V4 backslash pi 2 backslash eta backslash left plus T0 8 backslash frac 12 plus backslash left backslash frac backslash lambda plus T0 backslash eta 8 backslash frac 23 backslash frac 24 HGV backslash frac 387 backslash C dot 96 backslash frac 13 backslash pi backslash frac 43 backslash gamma LG backslash frac 13 8 backslash frac 16. Where asterisk lambda is shape factor. Surfactants. Many technological processes require control of liquid spreading over solid surfaces. When a drop is placed on a surface, it can completely wet, partially wet, or not wet the surface. By reducing the surface tension with surfactants, a non-wetting material can be made to become partially or completely wetting. The excess free energy sigma of a drop on a solid surface is sigma equals gamma S plus PV plus pi R2 gamma SL minus gamma SV. Based on this equation, the excess free energy is minimized when gamma decreases, gamma SL decreases, or gamma SV increases. Surfactants are absorbed onto the liquid-vapor, solid-liquid, and solid-vapor interfaces, which modify the wetting behavior of hydrophobic materials to reduce the free energy. When surfactants are absorbed onto a hydrophobic surface, the polar head groups face into the solution with the tail pointing outward. In more hydrophobic surfaces, surfactants may form a bilayer on the solid, causing it to become more hydrophilic. The dynamic drop radius can be characterized as the drop begins to spread. Thus, the contact angle changes based on the following equation. $$ backslash cos backslash left backslash theta. 8 equals backslash cos backslash left backslash theta 0. 8 plus backslash left backslash cos backslash left backslash theta backslash infinity. 8 backslash cos backslash left backslash theta 0. 8 backslash left turn backslash matheme backslash frac t backslash tau. $8. As the surfactants are absorbed, the solid vapor surface tension increases and the edges of the drop become hydrophilic. As a result, the drop spreads. Surface changes. Thumb upright equals 2.2 strands of an uncharged ferrocene substituted polymer are tethered to a hydrophobic silica surface. Oxidation of the ferrous groups produces a hydrophilic surface due to electrostatic attractions between the resulting charges and the polar solvent. Ferrocene is a redox-active organometallic compound which can be incorporated into various monomers and used to make polymers which can be tethered onto a surface. Vinylferrocene can be prepared by a Wittig reaction and then polymerized to form polyvinylferrocene PVSC, an analogue of polystyrene. Another polymer which can be formed is polyferrous carboxylate PFC-Ma. Both PVSC and PSCMA have been tethered onto silica wafers and the wettability measured when the polymer chains are uncharged and when the ferrocene moieties are oxidized to produce positively charged groups, as illustrated at right. The contact angle with water on the PFCMA coated wafers was 70 degrees smaller following oxidation, while in the case of PVFC the decrease was 30 degrees, and the switching of wettability has been shown to be reversible. In the PFCMA case, the effect of longer chains with more ferrocene groups and also greater molar mass has been investigated, and it was found that longer chains produce significantly larger contact angle reductions. Oxygen vacancies. Rare earth oxides exhibit intrinsic hydrophobicity, and hence can be used in thermally stable heat exchangers and other applications involving high-temperature hydrophobicity. The presence of oxygen vacancies at surfaces of Ca or other rare earth oxides is instrumental in governing surface wettability. Adsorption of water at oxide surfaces can occur as molecular adsorption, in which H2O molecules remain intact at the terminated surface, or as dissociative adsorption, in which OH and H are adsorbed separately at solid surfaces. The presence of oxygen vacancies is generally found to enhance hydrophobicity while promoting dissociative adsorption.